We'll do a quick little review. Behind me is a consolidated list, not complete by any means, but it shows some of the more important topics. Let's do a quick run through on this list. At the beginning of General Chemistry 1, you go through matter. Matter's anything that has mass and takes up space. And there's a couple of ways to classify matter. One is by what it's composed of. Is it a pure substance, meaning just an element or a compound containing one type of molecule? Or is it a mixture of substances like salt water, sugar water, brass? Does it have a mixture of substances in there? Another way to classify matter is by whether it's a solid, liquid, or gas. We talked a little bit about what the differences between solids, liquids, and gases are. Measurement and numbers are also very important. What are the measurement units that we use in chemistry? The units for length, time, mass, temperature. So you should know what those SI base units are. The length is the meter, time is second, the mass is the kilogram, and the temperature is the Kelvin. And you should also be able to convert from one type of length unit to another type. You should be able to convert from meters to picometers, from seconds to microseconds. Numbers. It's important to be comfortable in manipulating really large and really small numbers. In chemistry, we deal with really large numbers, 10 to the 23rd power, and really small numbers, perhaps 10 to the negative 23rd power. So you represent those numbers using scientific notation, and so you should know how to use scientific notation, also know how to handle significant figures. When you do calculations involving measurements and quantities, you need to keep track of your significant figures. In other words, the error in your measurements. Dimensional analysis is probably the most important mathematical technique in general chemistry. And if you master this, then you master pretty much the technique used in 75% of the math problems of general chemistry. So really important. We'll take a closer look on this topic in a few moments. Atoms, molecules, and ions kind of go together. The building blocks of matter. Ions are what you get when you either remove an electron from an atom or molecule, or you give it an extra electron or two. Ions. Chemical reactions, finally. Chemical reactions, we'll take a closer look at chemical reactions, probably do a calculation involving the stoichiometry of a chemical reaction. Gases are very important. They're all around us. And in general chemistry, we study gases in fairly good detail. You might remember the ideal gas law, Dalton's law of partial pressures, maybe some of the other gas laws. Thermochemistry, part 1. This deals with the heat and energy changes of chemical reactions. When we get to the thermochemistry component of general chemistry 2, we will review thermochemistry part 1 in pretty good detail. The atomic structure. What does an atom look like if you were to break out your so-called atomic magnifying glass? Well, you might remember that an atom has the protons and neutrons in the middle, in the nucleus, and it's surrounded by electrons, and these electrons occupy orbitals around the nucleus. So maybe you remember what those orbitals look like. Hopefully you remember something about them. If you understand the orbitals, then you really understand electron configurations, because electron configurations is a shorthand notation of the orbitals occupied by the atom. Electron configurations is the way the periodic table is laid out. atoms are laid out on the periodic table based upon what their electron configurations are. So atoms that are in the same column contain the same number of valence electrons, outermost electrons. And those outermost electrons are the most important ones when it comes to chemical reactions. Lewis structures is a very important topic for those of you who are going to be studying organic chemistry or biochemistry. You really want to understand Lewis structures. And it would be helpful to go ahead and review that on your own, how to draw a Lewis structure properly. We'll take a closer look at Lewis structures, but more in particular, molecular shapes. If you know the Lewis structure, in other words, if you know the connectivity, what atoms are connected to which, then you can use that information to get the molecular shape. And once you know what the molecular shape is, you can tell whether or not the molecule is polar. So polarity is also a very important topic. Polarity deals with, does the molecule have a negative end and a positive end? Is it polar? And that's pretty important when it comes to general chemistry too, when we start talking about intermolecular forces. We'll take a quick review of molecular shapes. Dimensional analysis is a powerful technique used in many areas of science, and it's also used a lot in general chemistry. It's basically a calculation process that is used to convert one type of unit into another, or build a particular type of unit. Here's an example of converting one unit to another. Suppose you want to convert 5.22 milligrams to kilograms. Now, in order to get from milligrams to kilograms, you need to know the relations between them. A milligram is related to a gram through the following relation: 1,000 milligrams equals a gram. And gram is related to kilogram through this relation: 1,000 grams equals a kilogram. Now, these relations can be used to build what are called conversion factors. And conversion factors have the following property: the numerator is the same in quantity as the denominator. So a gram equals 1,000 milligrams. And when you multiply by a conversion factor, it's like you're multiplying by 1. So let's see how it goes. 5.22 milligrams multiplied by 1 gram divided by 1,000 milligrams. When you multiply by this, the milligram units cancel and you're left with gram. And then multiplied by the second conversion factor, 1 kilogram divided by 1,000 grams, and here the gram unit cancels. So doing the whole process means canceling the milligram unit and canceling the gram unit and being left with a kilogram unit. So 5.22 divided by 1,000 divided by 1,000, you get 5.22 times 10 to the negative 6 kilograms. Another example is right here. Suppose you want to convert 10.5 grams per centimeter cubed to micrograms per millimeter cubed. Now here you have a derived unit where there's a unit in the numerator and a unit in the denominator. And in order to do this conversion, you need to convert both the numerator and the denominator. And also you need to know what a microgram is. So the relation between grams and micrograms is 1 gram equals 10 to the 6 micrograms, or a million micrograms. Okay? This relation will allow you to convert grams to micrograms. Now, to get from centimeters cubed to millimeters cubed, this is a unit of volume. Well, the relation between centimeters and millimeters is as follows. You know that 1 meter equals 100 centimeters, and 1 meter also equals 1,000 millimeters. So you could say that 100 centimeters equals 1,000 millimeters. Now, You could also write 1 centimeter equals 10 millimeters, and you could get that by dividing this first relation by 100. If 1 centimeter equals 10 millimeters, then 1 centimeter cubed equals 10 millimeters cubed. When you cube a measurement, you need to cube both the number and the unit. So 1 centimeter cubed equals 1 cubed, which is 1 centimeters cubed. And 10 millimeters cubed equals 10 cubed millimeters cubed, which is 1,000 millimeters cubed. So you have here your two relations that connect the starting unit to the ending unit. So let's see how they go. You use the relation to build the conversion factor. So you convert one unit at a time. Let's convert the numerator unit first. 10.5 grams per centimeter cubed multiplied by this conversion factor, which is 10 to the 6 micrograms per gram. And when you do that, you cancel the gram units, and you're left with microgram up top. Multiplying by the second conversion factor, which is 1 centimeter cubed over 1,000 millimeters cubed. And multiplying by that conversion factor means canceling the centimeters cubed down there with the centimeters cubed up there, and you're left with millimeters cubed in the bottom. So doing both multiplications leaves you with units of micrograms per millimeter cubed. And when you do the multiplication, you get 10,500 micrograms per millimeter cubed. Notice that the 5 is underlined, which indicates that you have a 1, 2, 3 significant figure number in the result. If you start with 3 sig figs, then you'll be left with 3 sig figs. I will usually be denoting significant figures with an underline under the last significant figure. Another way to represent this calculation is perhaps a little bit more concisely as follows. The first part is the same, but when you convert the volume unit, all you have to do is use this conversion factor where 1 centimeter is up top and 10 millimeter is down underneath. And then you cube the entire conversion factor, which means you cube everything up top and you cube everything underneath. And it works out the same way. And so your answer comes out in scientific notation again to 1.05 times 10 to the 4th micrograms per millimeter cubed. Let's do 2 examples where we have to build the unit required by the solution. In the first example, we're asked, how many minutes does it take light from the sun to reach Earth? Now to answer this, we need to know how far the sun is from the Earth, and that's a distance of 93 million miles. We also need to know how fast light travels. It travels at a speed of 3.00 times 10 to the 8th meters per second. Starting with distance, 93 times 10 to the 6 miles, we can convert that distance to feet using the following relation. 1 mile is 5,280 feet. Then we can convert feet to inches, inches to centimeters, centimeters to meters. Then using the speed of light, we can convert meters to seconds. When you're talking about light, 3.00 times 10 to the 8th meters is the same thing as 1 second. Then finally we can get from seconds to minutes. So stringing all of these relations together, we see it'll take 6 steps. So converting the relations into conversion factors, we start with distance, 93 million miles, convert from miles to feet, feet to inches, inches to centimeters, centimeters to meters, meters to seconds using the speed of light. Now notice here we convert from distance units to time units. And then finally, from seconds to minutes. When you do all the calculations, you end up with 8.31 minutes. This is a 2 significant figure answer because we started with 2 significant figures at the beginning with the distance. If you want to, you can convert to minutes and seconds. So it's 8 minutes, 19 seconds. In the second example, we're asked how many grams sodium chloride are dissolved in 7.31 milliliters of 0.212 molarity solution. You remember molarity tells you how many moles per liter. So we can start with the volume here and convert from milliliters to liters, and then using the molarity we can convert from liters to moles of sodium chloride dissolved. 1 liter is the same thing as 0.212 moles of sodium chloride. And then finally we can go from moles of sodium chloride to grams using the molar mass. For sodium chloride, 1 mole is 58.44 grams. We see this will take us 3 steps, so that means 3 conversion factors. Starting with the milliliters, we convert that to liters, then convert the liters to moles, moles to grams. And we end up with 0.09057 grams. Notice how there is 1 extra digit kept after the last significant figure. Although this is going to be a 3 significant figure solution, it's often desirable to keep 1 more digit after the last sig fig, because you may end up using this result in a later calculation. And in that case, it's good practice to not round the solution yet. In chemistry, we spend a lot of time talking about chemical reactions. After all, they are the central focus. So let's take a closer look. A chemical change is called a chemical reaction, and a chemical reaction is described by its chemical equation. Here's an example of an equation that describes the reaction that occurs between methane and oxygen. Methane reacts with oxygen to produce carbon dioxide and water. The chemicals that you start with are called the reactants, and those that you end up with are called the products. Now, there are a couple of interpretations for this equation. One is the molecular interpretation. You would say that 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. That might be the simplest interpretation, but a more useful interpretation may be the mole interpretation. And you could say that 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. You should remember that a mole is the same thing as 6.022 times 10 to the 23rd. So when we talk about a mole of methane, we mean 6.022 times 10 to the 23rd molecules of methane. So that's quite a lot. Now, a couple of other things that you want to notice about chemical equations. Another one is the states of each of the chemicals are indicated in parentheses. In this case, they all happen to be gases. And also, you see that 2 oxygen molecules are required and 2 water molecules are produced. Why can't it be methane reacts with oxygen to produce carbon dioxide and water? Well, because when you have a chemical reaction, the number of atoms that you start with needs to be the same as the number of atoms that you end up with. So if you start with 1 carbon, you need to end up with 1 carbon. And if you start with 4 hydrogens, you need to end up with 4 hydrogens. That's why you need that 2 there. 2 water molecules would give you 4 hydrogens. So that process of adding coefficients to balance the number of atoms that you start with and end up with is called balancing the reaction. This is a pretty simple one to balance. You just need a 2 right here and a 2 over there. If you recall in general chemistry, some of the reactions are quite difficult to balance. And with chemical reactions, you can ask a lot of questions. Perhaps the first question that you ask is, if you start with a certain amount of reactant, how much product should you expect to get? So here's a question. How many grams of water are formed if 10 grams of methane reacts? Now, this is an example of trying to build the units required in the result. You're trying to get to grams of water, so that's what you want to end up with. And what it gives you is 10 grams of methane, so that's going to be what you start with. So let's see the conversion factors that we use in order to answer this question. You see, that's a difficult question to answer right away, because the reaction doesn't tell you how many grams of water you get from how many grams of methane. It tells you that 1 mole of methane gives you 2 moles of water. So we need to convert grams of methane to moles of methane before we can answer this question. So that's the first thing that you want to do. Take your 10 grams of methane and convert it to moles. 1 mole is the same thing as 16.04 grams. Then, after you multiply by this conversion factor, you have moles of methane. And we know that 1 mole of methane will give you 2 moles of water. When you're talking about this chemical reaction, 1 mole of methane means 2 moles of water. So this is the stoichiometric conversion factor. After you get this far, you've converted to moles of water, but we need to get to grams of water. So you multiply by the following, 18.015 grams per mole. And here the moles of water cancels, and you're left with grams of water. And when you do the entire calculation, you end up with 22.46 grams of water. It's a 3 sig fig number. In the previous question, it was assumed that all of the methane reacted, but sometimes that's not the case. Here's another question which asks, how many grams water are formed if 10 grams of methane and 10 grams of oxygen react together? Now, it's unlikely that all of the methane and all of the oxygen fully react. Chances are that you have too much of one of them and not enough of the other. So there are a couple of approaches to solving this problem. Perhaps the simplest one is just to assume that all of the methane reacts and figure out how much water you get from that. And then to do the problem again, assuming that all of the oxygen reacts, and then figure out how much water you would get from that. So let's do this approach. If you assume that all of the methane reacts, then we've already done this calculation on the last slide. 10 grams of methane, you convert it to moles, convert moles of methane to water, and then finally moles of water to grams of water, and you would expect to get 22.5 grams of water if all of your methane reacts. Now, if you assume all of the oxygen reacts, then you would convert 10 grams of oxygen to moles of oxygen. 1 mole is 32 grams. And then 2 moles of oxygen gives you 2 moles of water because of the coefficients 2 and 2. And then you would convert moles of water to grams of water. And doing this calculation, you see you would end up with 5.63 grams of water. It turns out this is the answer. You see, oxygen is what limits the amount of water produced. If all of your oxygen reacts, you would get 5.63 grams of water. So you know that you're not going to get that much water because all of your oxygen would only give you this much. So this has to be the answer. So it turns out that oxygen is a limiting reactant and methane is an excess. Knowledge of the structure of a molecule can be useful in many areas of chemistry, and it's important to be able to get this information using just the molecular formula. Let's see how this is done. Now, the Lewis structure is used to predict the shape, so we need to get the Lewis structure first. We don't have a lot of time to go into how to get the Lewis structure, But I will tell you that a good approach is to just lay the pieces of the puzzle out and start connecting them together until you get the proper answer. Our first example is methane. The formula for methane is CH4. So here are the pieces of the puzzle. You got your carbon surrounded by the 4 valence electrons, and the 4 hydrogens each surrounded by 1 valence electron. When these pieces are arranged properly, you end up with carbon being in the middle, surrounded by the 4 hydrogens, and connected through a single covalent bond, which is really 2 valence electrons being shared between the carbon and the hydrogen. Now, when the center atom is surrounded by 4 groups, those groups are arranged in the shape of a tetrahedron. So this is a tetrahedral molecule, and it's nonpolar. There is no negative end and no positive end in this molecule. Our next example is formaldehyde, CH2O. Here are the pieces of the puzzle. And when they're arranged properly, you end up with carbon being in the middle, single bonded to the 2 hydrogens, and double bonded to the oxygen. Carbon has 3 groups around it, so it's in the shape of a triangle, and this is called the trigonal planar structure. Now, oxygen is the second most electronegative element on the periodic table, so it pulls electrons towards its end of the molecule. So this molecule does have a dipole, and it's described as being polar. Carbon tetrachloride. Here are the pieces of the puzzle, and arranged properly, you get carbon surrounded by the 4 chlorines. This is another tetrahedral structure. Now, chlorine is electronegative, but since you have 4 chlorines surrounding the carbon in a symmetric fashion, it's like a 4-way tug of war, and the electrons end up not being pulled anywhere. So this is a nonpolar molecule. You can have more complicated, rather interesting examples of molecular shapes. Benzene, the formula for benzene is C6H6. And this is a nice symmetric shaped molecule where each of the carbons is single bonded to a hydrogen and then connected to 2 other carbons. So each of these carbons is surrounded by 3 groups, therefore trigonal planar. This carbon's trigonal planar and the rest of them are too. And the entire molecule ends up being flat. Ethanol, the formula for ethanol is CH3, CH2OH. The formula being given in that fashion because you're trying to be guided towards the correct structure and shape. Ethanol, when you draw its structure, you end up having your CH3 group, CH2 group, and OH group. This carbon is tetrahedral. This one is too, and the oxygen is bent. There is a dipole in this molecule pointing towards the oxygen. It might be difficult to know exactly which way the dipole points because single bonds can rotate around one another, so this molecule is somewhat flexible. But it is polar, and there is a negative end and a positive end. The amino acid glycine is a more complicated example. Formula is NH2, CH2, COOH, and the structure looks like the following. You have your NH2 over here, your CH2, COOH. Your nitrogen has what's called a trigonal pyramidal structure, and that's like a tetrahedral structure except one of the positions is occupied by a lone pair, so it ends up being trigonal pyramidal. This is a tetrahedral carbon, a trigonal planar carbon, and then a bent oxygen. This is definitely a polar molecule. You have several electronegative elements here, your nitrogen and your 2 oxygens. So that's just a quick look at molecular shapes. Molecular shapes will be important when we get into intermolecular forces in our next lecture, and I hope you join me for that. Thank you.